Right, hi everyone, this is Dr. Kao. Welcome. So let's move on to the implementation part of the logistic regression. So first of all, you need to go to the course website and download the Jupyter notebook. So I already opened that in my computer. So now, first we take a look at the examples. So as you can see here, we do have the data. The tuples would be the input data. Each of the element is a tuple. That is the tuple describes the experience. So the first number is the experience. Second number is salary. The third would be paid or not paid. So obviously the number third element would always be 0 or 1. And then the data, we just get each of the element into the list. The x-axis and y-axis, the x-axis would be the list of 1, experience, and salary. So we get it from the data. The y would be the paid account. So this is the output. So keep in mind, like the logistic function, the model we have, we use it here, right? So we use y equals f xi beta. So the f is a logistic function. And what is the beta and the xi? So the xi is actually xi would be here, right? So we have the 1, experience, and salary. And then the beta would be beta 0, beta 1, beta 2, right? So xi x times beta. So that's similar to the multiple linear regression model, if you still remember, just like this one. So it's similar to this formula. We just use the vector to describe that. And in addition to that, you apply the f function to that result. So the result will be always between 0 and 1 because f is a logistic function. And the result, so the result will be always 0 and 1. So here is an implementation of the logistic regression. It's quite straightforward, and the logistic prime. And I can just run those. So I'm going to run the first one. I'm going to run the second one for the logistic function. So now we need to get the gradient descent. So keep in mind, like in the part 1, we described the log likelihood, right? And to maximize that is same as minimize the negative log likelihood. So here is the implementation. You just need to check this one. So this is a function that's going to calculate the negative log likelihood for the x, y, and beta. And it's going to call the function here. So this function is going to calculate the negative log likelihood for one data point. And then you are going to sum up them. So the sum of all of them, that will be the total negative log likelihood. So this is the function we have. We need a little bit calculus for the gradient descent algorithm. So we need to calculate the partial derivative. So the log likelihood gradient, we get it here. So it's a vector sum of each of the negative log gradient. So we call this function that's going to calculate the gradient for one data point. And then this one data point, we need to call the function to get the jth partial derivative for one data point. So generally, it's just going to calculate the gradient descent for each of the data point and then put them together. Okay. So now that's it for the gradient part. Now we can apply the model. So we first need to make sure you have the Scratch folder downloaded. And we also include several of the functions or libraries from the Scratch. And then there are some function here. It's going to do the scale. So especially for each of the data point, we try to scale them so they have the similar mean and the standard deviation. So this is a scale function, and we have the rescale function. Rescale function is going to rescale the data set. So the data would always have the mean of 0 and the standard deviation of 1. So as we know, like some of the data point, their mean could be more than like 100 or 1000. So this function is generally try to rescale them. So all the data points, they are in similar range. Okay, and now if you still remember the function train test split, that's a very important function that's going to split the dataset into training and testing, right? I think we ask you to implement that in one of the homework. You probably can find it out. It's also in the slides. So here we apply the rescale function to rescale the input axis. So it will be scaled to the mean and the standard deviation of 0 and 1. We use 33% for the testing and 77% for the training. Learning rate, we just make it 0.01 for the gradient descent. For the beta, we randomly just assign a number. We start with a random number, and then for each epoch, we are going to apply the gradient descent algorithm, get the gradient, and then update the beta. So this is going to update the beta, and then we calculate the loss and print it out. So it's quite similar to the multiple linear regression model we just learned. So it's apply the same thing. So I'm going to just run this one. I need to make sure I run everything. Okay. Make sure you run from the beginning. So you have all the function and import all the libraries. So now it's running. We use a TQDM, so that's why it's going to show you the time. So we have 20%. I think it should be fast. We just make 5,000 epochs, and the learning rate is 0.01. So generally, like this implementation, we already have most of the functions. We learned that before, and we directly call them, so you don't need to implement that from scratch. So overall, like from the beginning, like we have the logistic regression, the data here, and then we need to have this function. We have to implement that. We implement the gradient descent, the negative log likelihood, and the partial corrective, especially the gradient part. So this function will be used to for the gradient descent algorithm to update that the beta, right, to minimize the loss. So we apply the model. So I think it's almost done. Okay, so once it's done, I print the beta. So this is the final beta we got. So now your model is actually your model is something like, I can just print it. So your model now is y would be, right, would be the f, and then your x as the input times the beta. We have it here. So this would be the beta. This would be the beta. Okay, so this would be beta. So that means it would be the beta 0. But beta 0 is this one, right? And then plus beta 1 times your experience. So experience plus the beta 2 times the salary, right? Times the beta 2. Okay, and then we calculate the number. But as I said before, the multiple linear regression directly do that, but this result could be more than 1 or less than 0, right? So we apply the logistic function to that, so the result will always between 0 and 1. And then based on this y, you can make predictions. So now you can say like larger than 0.5 would be 1, less than 0.5 would be 0. So here we get the mean and standard deviation for the scaled one, and we also get the unscaled one. So there are some difference, and as we explained, like we just scale them, so it will be between 0 and 1. But of course, we can transform them back to the original data. So this is beta unscaled. So the scaled one, we have it here. This is after we scale the input, right? So it's here we call rescale. After we rescale the input, that's a beta we got. But if you didn't rescale that, you probably need to get this beta unscaled. So now let's just take a look at the model, like how good is that, how is the performance. So we can just have the calculate the true positive, false positive, true negative, and false negative. We initialize with 0. This is just do some simple counting. We apply that, the prediction, right? We apply that to the testing data set. So as I said, we just need to apply the dot multiplication of beta and xi, right? And then this prediction, if it's larger than 0.5, then we predict it as 1, right? So this is just saying, like, if it's yi, this is actual is 1, and your prediction is larger or equal than 0.5, that means you make the right prediction. So we update the true positive. Else if yi is still 1, that means your prediction is wrong, right? So we get false negative. Else the prediction, if your prediction is 1, but y is 0, then we have false positive, otherwise true negative. So your final precision, you can just use the counting, like the stats you just counted, and then we can predict it here is 0.75 and record is 0.8. Not too bad. So that means we're doing something quite okay. We could plot them right now, so we can just see this plot. So that's all about the demo for the slides. I think I can run them. I forgot to run them. Okay, now I can run them. You can do that also.